let's go ahead and continue with chapter 9, all about that atomic physics. So, in part 1, we were talking about a little bit of the history about how the idea of the atom had developed from the ancient philosophers up to Dalton. We talked about Thomson, Rutherford, and now we're going to change gears just a little bit and see how some other developments about light is going to influence um, the idea of the atom. Let's go. So we're going to see kind of how some other areas are going to affect the idea of the atom, and to do that, we have to go to a guy named Max Planck. He was dealing with looking at energy and a thermal oscillator, and so he was saying how this energy, it wasn't a continuous amount where you could get just you could pick any amount that you wanted. It would only happen in discrete amounts, and he called those discrete amounts quantums. So that's where this term quantums comes from. Um, and so energy is quantized means that energy is released in discrete amounts. A little side note, kind of interesting. His second son was actually executed by the Nazis for trying to help come up with a way to um, assassinate Hitler. So you never know how all these things kind of intertwine with one another. Okay, so back to this. So we get this idea that light and electrons both have this quantized energy type association. And so what we learned is that light and electrons can act as both a wave and as a discrete particle. Now, that's kind of opposite of one another. A wave, we usually talk about it as being continuous, and particles are definitely not continuous. Um, but light and electrons have properties of both. And so we can actually set up experiments to study those different parts. Now, here we have another term. We have the term photon. Photon just means a quanta. Remember, that means a discrete amount of, it says a quanta of EM. EM stands for electromagnetic radiation. So remember, we talked about that before. That's like your light from the sun, anything from radio waves, light waves, um, gamma, X-ray, UV, infrared, all those are different types of EM. If you have a discrete amount of EM radiation, we call that a photon, and Einstein is the one who came up with that. On the bottom, we have a couple of pictures that are supposed to be trying to help us kind of make amends to kind of wrap our minds around this idea that light and electrons can be thought of as both a wave and as a particle. And we've had people get Nobel Prizes for proving it's a wave, and his son came back and got a Nobel Prize for proving that it's a particle. Yeah, it's all good. So remember that the same phenomena will happen with both light and with electrons. But it's a lot easier for us to be able to start by looking at light. So here's an example of something that's what's called a continuous spectrum. When I was a little kid, I was so jealous of my best friend because she had a prism that she could hang in her bedroom window. And when the light would shine in just right, she would have rainbows all over her bedroom. And I thought it was just like the coolest thing ever. That is a continuous spectrum. So what we do here is we take what's called white light. White light just means it has all of the different colors and all of the different wavelengths actually contained within this. Light from the sun is white light. Light from incandescent sources like a regular old-fashioned light bulb, that's going to be a white light also. So over on the left, we have that white light source. It's going to produce light. We take a very thin sliver of that. We send it through a little slit, and then we're going to send it through a prism. So the prism, what it does is it's going to cause it to disperse into its different wavelengths. So then we get all of the colors of the rainbow. down below. So we have our purple, which is going to be like 400 nanometers, all the way up to the red, which is going to be like 700, 750 nanometers. So the violet or the purple have the really short wavelengths, and the violet has the much, I'm sorry, I said that one wrong. Almost said it right. The violet has the really short wavelengths. The red has the really long wavelengths. And so we can get into energy and all sorts of stuff we've seen in previous chapters. But we're just really concerned about the colors for right now. So remember, this is a continuous spectrum. We have all of the colors, all of the wavelengths, and then that's going to relate to all the different types of energy levels. But what happens if we don't have white light at the beginning where it has all of these different wavelengths? What if it's something that has only certain amounts? So let's see what that would look like. Okay, so what we have here, these two, look at the pictures that we have up there. Notice they're kind of like opposites of one another. These are called line emissions and line absorption lines. The one on the left, that's your line emission. It's only going to produce certain lines. The one on the right, the line absorption, we have certain lines that are missing, but you'll find that the lines are in exactly the same places. Now, the difference between these two, or how they can set these two up, it depends on what your light source is and if you send it through anything. So what the one I normally do in class is the line emission, the one on the left. So if you notice, the light source, instead of being white light this time, is actually excited hydrogen gas. So what happens? We excite the hydrogen gas. We do that by running electricity through it, and so it produces a light. Now that light, we send it through the slit, send that light, so it's just a very thin sliver of it. We send that through the prism. It's going to separate it into the different wavelengths, but notice we don't have all the wavelengths anymore. We only have a couple. There's 4 very distinct lines that you'll see, and then if you do this one in real life, there's a couple of additional ones that you may see faintly, but very definitely we have 4 very distinct lines. Now, if you look at the line absorption, the one on the right, this one they start with white light, like we did for the continuous. We get a very thin sliver of that, and then we send that through cooled hydrogen gas. So what's going to happen here is it's going to absorb those certain wavelengths. And so then the light that passes through will have all of the other wavelengths. So we can see all the other colors except for those 4 distinct lines. So line emission, line absorption, they are both getting into the idea that different elements, something's happening with light as it interacts with that element. So let's see if we can find a theory as to explain why that happens. So we have the idea that light that comes from hydrogen isn't continuous. It doesn't have all the lines. It only has certain wavelengths of light. Again, that's what we're showing in that bottom left-hand corner. There's only certain wavelengths, only certain frequencies, only certain energies that are associated with that hydrogen. And it turns out every element looks completely different. Now, the one who tried to explain this was Niels Bohr. He has what's called the planetary model. His theory was okay, so remember we had just had the nuclear model where we have a nucleus and the electrons are around the outside somewhere, but we don't really know what they do. Now what we're going to do is we're going to revise that and say that the electrons move in circular orbits around the nucleus. And depending on how far away that orbit is, there's a certain amount of energy that's associated with it. Now, on the bottom right, we have this kind of explanation of trying to explain why that happens. So in the center, we have the nucleus. We're going to excite the electrons. So the electrons are going to go to a higher orbit. Later, sometimes they call them quantums, a higher shell. We use shells a lot of times now whenever we talk about this. So it's going to go to a higher level, a higher shell, higher orbit, whatever you want to call it. It could jump 1, it could jump 2, it could jump 3. But they don't want to stay at those higher levels. So when the electrons fall back down, they release a certain amount of energy, and that's based on how far they fall. If it's from the second to the first shell, the third to the first, the third to the second. So Bohr was able to explain what happened in each of these cases. So let's see here. Let's jump ahead to the next slide. And this, we have a picture on the top where we have this idea that electrons, as they fall to different levels, will release certain amounts of energy. And that is why we have the certain spectral lines. Now, I like to talk about Bohr. He's such a fascinating person. All these guys are. So, just a little bit about Bohr. His brother Harold was an Olympic soccer player for Denmark, and he was also a mathematician. Now, Niels Bohr, the one that we're concerned about, um, he was a student of Rutherford, and remember, he's the one that had that nuclear model. So we're just expanding, we're revising little bits at a time as we find out more information to make a more accurate model. He ends up getting a Nobel Prize in 1922 in physics. He actually debated Einstein over this idea of duality. Einstein was more worried about like the science behind it. Bohr has a very mathematical mind. He wants to make sure that the equations work, and the equations work great for hydrogen. But anything other than hydrogen, we have to add something more to this theory. A little bit more. So about when World War II starts rolling around, Niles here has a little bit of a problem. He is Jewish, so there's this story about how he was evacuated from Stockholm in an unarmed fighter bomber. He didn't put on the proper oxygen equipment. He actually passed out, almost died on the way out of there. Now, he escaped to London. There's rumors that he worked on what's called tube alloys, which is their nuclear program. We've also heard stories that he ended up in the U.S., going to Los Alamos, assumed the name Nicholas Baker, and was a knowledgeable consultant on the Manhattan Project, which of course was our nuclear program. He felt that all countries, including Russia, should share information about weapons. I don't know about that part necessarily, but just a fascinating person. So, planetary model. The electrons move in circular orbits. But again, this does only works for hydrogen. It's not working on anything more complex. So let's see what they're going to do next.